Okay, folks, welcome to the CA to DM Homely Atmosphere online seminars. Chaos for all of us. Um, it's a pleasure to be here, being my own host on this seminar, where I'm going to talk about dimensionality in material science. First of all, I hope all of you are safe at home, healthy, and I hope you enjoy what I'm going to talk about. I want to warn the experts that my seminar today will be, I will try to reach everybody. It's not going to be a technical seminar. It's going to be more of a vision type seminar where I'm going to talk about the importance of dimensionality in the properties of materials. So I'm going to start with sharing my screen. There you go. So Bernice, Marilyn, can you see my slide now?
Yes,
Yes.
I can see.
Okay. All right. So let me start my seminar talking about the beginning. The beginning actually can be set more or less at the late 19th century, early 20th century, where people are doing measurements of the spectra of black body in thermal at some temperature. And what they see is shown in this picture here. So this is what's observed for a body at 5,000 degrees Kelvin as a function of the wavelength of the radiation coming out of the body. And this is the expected behavior until that point in time. And when people looked at this, they were flabbergasted. They could not understand why at short wavelengths, right? So, which means at higher energies, why there was this huge deviation from what the classical theory predicted. And then nobody knew. This was a mystery for a while until this gentleman, Max Planck, um, wrote this paper in 1901, where it's in 1900, exactly at the beginning of the 20th century, where he essentially could explain the black body radiation by assuming first that the energy was proportional to the frequency. And then for the first time, he introduced a constant that now it's known famously as Planck's constant, and that the energy, the statistics associated with the electromagnetic energy was discrete. And then he came up with this formula number 13 of this paper, where he could explain this data extremely well. But at that time, this explanation was not based on any fundamental theory. It was more like a mathematical exercise. By the way, Max Planck was a theoretical physicist, and nobody knew why light would behave in this way and why we need to introduce a new universal constant into the understanding of the universe. And notice here that he says H and K, this is are universal constants, but he doesn't say from where this is coming from. So this is a piece of history which is very interesting and to motivate you to understand that in science, sometimes you don't know where things come from, and it takes a lot of work to understand these things. So later, more or less at the same time, people were measuring a related experimental question, which is the the electromagnetic spectrum of a gas when you pass a current through a gas. So this is like a glass tube with gas inside, and then you run an electric current. You collect the light of this gas, this glow, and then you pass through a prism, and you see the spectrum. And the interesting thing is that different gases have very sharp lines at different wavelengths, and you had all different series of emission spectra of these materials. And this was a huge mystery for everybody. Why light coming out of a gas that is being bombarded by electrons passing a current would emit these in these particular frequencies, like they have their own signature. So they did not understand. But this essentially is what inspired many theorists to look into this problem from a deeper perspective. And then this is when quantum mechanics appeared. So if you look at quantum mechanics, it starts with a very mysterious Greek letter called psi, which is called the wave function. And this wave function, it's not necessarily, it's not something you can measure in an experiment. It's a complex function. And it's most, let's say, ordinary interpretation is that its modulo squared, which is a real number, is the probability of finding a particle or an electron at a certain position in space. And it obeys an equation called the Schrödinger equation, who essentially he proposes equation to describe the behavior of electrons in atoms. So essentially what Schrödinger did is that he took this equation, it's a differential equation, he put the Coulomb potential for electron moving around a proton, the simplest element we have, which is hydrogen, and he solved this. And by solving this, he found that the solution of this equation essentially produces discrete energy levels that could be numbered from 1 to infinity. And then he realized that that spectra that was observed in a glass tube could be described in terms of transitions of electrons between different quantized states. So by comparing that with experiment, Schrödinger was able to describe the experiments of its time, like the Lyman, the Balmer, the Paschen series that were measured in all these experiments. But also what it provided for us is this concept that the electron is not, it doesn't behave very much like a particle. In many ways, it behaves like a wave, and in fact, it behaves as both. And if you look at the plots of these wave functions that solve the Schrödinger equation for the hydrogen, you find these beautiful patterns starting from the first, the ground state, and then all the excited states. And clearly you can see that these wave functions, they have well-defined shapes with well-defined symmetries. And this is very important in order to understand the behavior of materials. So the solution of the Schrödinger equation, the introduction of the wave function, and then the description of these experiments was essentially fundamental for everything that came after it. So essentially, the basis of everything we understand today about the way materials behave come from this very basic structure. So let me just jump to an atom that is very close to my heart, carbon, right? So carbon, it has a nucleus with 6 protons. It has 6 electrons around it. And the way you think about this is that the states are filled with electrons, and each state can only be filled with 2 electrons, one with spin up or down. So spin is the magnetic moment of the electron. So one of the laws of quantum mechanics is called the Pauli exclusion principle, that says that for each state, you can have only 1 electron. So either we spin up or spin down. So in order to understand the atoms, you have to understand how you fill the shells of this atom in the hydrogen atom structure with electrons. And in the case of carbon, essentially you have 6. So 2 electrons are in the lowest energy state, which is a very deep state. It's very close to the nucleus. So it's very tight to the nucleus. And then you have these other 4 electrons, which are in the next state, which is n equals 2, which has s and p orbitals. So essentially, you have available 8 states there, but you have 6 electrons, which are in the outer shell of carbon. And it's essentially these electrons which are responsible for the binding of carbon, the way carbon binds to other elements, the way carbon binds to carbon itself. As I showed before, these states, they have certain geometry. So that geometry is responsible for the structure, for the geometry, dimensionality of the materials. So if you take now 2 carbon atoms and approach them, they will not necessarily bind to each other. The reason is that the carbon atom is a neutral object. So, and the forces between neutral objects is a very weak force called the van der Waals force, which essentially does not guarantee that you form a strong bond. So it means that, in fact, there is an energy barrier that separate 2 carbon atoms that make them, it makes difficult for them to bind. But then another quantum mechanical effect comes into play, which is called quantum tunneling. So in quantum mechanics, there is always a probability that the electron can pass through a barrier. Or another way, this is the particle version of it. Another way is to think in terms of wave. It's always possible that the wave function of the electron penetrates over the barrier. And in this case, electrons are actually capable of passing from one atom to another and form a bond. They form a bond, their energy is lowered because they share the electrons. And by sharing the electrons, they reduce their energy. By reducing the energy, they can form a stable molecule. So this is essentially the basis of the covalent bond. And because these wave functions have certain geometry, in carbon, you can have different types of bonds, between atoms. And they are classified by what's called hybrid orbitals, which are combinations of S and P states. Because I told you this S and P states, they of the n equals 2 level are very close in energy, so they can combine among themselves to hybridize and lower the energy of the molecular bond. And you can see in this picture here, the arrangements can be linear, trigonal, tetrahedral, pyramidal, octahedral, and so on. So it's pretty obvious from this that you can have many different types of dimensionality in this problem. If you have the sp bond, essentially the whole thing is going to be one-dimensional. If you have a trigonal structure, which is planar, you end up to having a planar structure. If you have anything like tetrahedral, trigonal, or octahedral, you can form three-dimensional structures. So you have to understand then that the dimensionality, the geometric structure of these materials come from this very basic physics, which is the hydrogen atom and the tunneling, or the covalent bond. And one of the people who most influenced in this area was chemist Linus Pauling, who actually got the two Nobel Prizes, one Nobel Prize in chemistry for his work on understanding the structure of materials, and another one for peace, because he participated in the anti-nuclear protests during the Cold War time. So this is just to give you an idea that everything is born out of this very basic principles of quantum mechanics, and dimensionality comes from that. So, but when you're talking about materials, and we're talking about solids, and we're talking about molecules, you have to think about many atoms, right? So imagine now I have a chain of carbon atoms like here in this figure, right? And let's assume that there is a huge energy barrier between them and they cannot share their electrons. In that case, we know the solution. The solution is essentially the isolate carbon atoms. We're going to have an atomic distribution of energy levels according to this diagram, and everything is going to repeat as many atoms I have. So if I have an Avogadro number of atoms, say 10 to the 23, I'm going to have 1023 copies of the same spectrum given by the hydrogen atom. Now, from the previous slide, if now the electrons are allowed to jump from atom to atom, you expect something new to happen. So because now essentially the electrons can be shared among all atoms and now we have a solid or a polymer or something like that, right? In that case, what happened is that the states, original atomic states, which were 10 to the 23, they remain 10 to the 23, but now they are indexed by a different quantum number, which is called crystal momentum. So crystal momentum is essentially the momentum of the wave, the electronic wave moving in the solid. So here is an example. So from the 1s state, you get what's called a 1s band. And then from the 2s, 2p, you get 2s, 2p bands. Okay, and for each momentum, you have a different state. However, in this region here, I still have the original 10 to the 23 states I started with, right? And this concept of bands and crystal momentum, essentially in a material that has crystal symmetry, which means you have a motif that repeats over and over and over and over again, 10 to the 23 times, essentially creates what's called a crystal. And this gentleman, Felix Bloch, he essentially initiated the whole field of what's called solid state physics by proving that exactly that if I start with atoms together and I have a periodic potential created by the atoms, I'm going to get bands. So he found a way to classify the states in a crystal in terms of bands, which come back from the atomic states in the material and from the crystal momentum. Essentially, is the fact that the tunneling allows the electrons to move freely through the entire crystal. So dimensionality also plays a role here. And this idea, this concept, it's what essentially allowed us to understand why materials behave in different ways. So going back to that band diagram that I showed you before, this is essentially the energy and the crystal momentum, and these are the different bands. And then if you look under a microscope, say around here, what you would see is not really a continuum. It would be discrete states separated by very small amounts, which have to do with the size of the crystal. And if you blow it more, you would see that these states, actually, they are discrete. But the energy difference between adjacent states is so tiny because I have such a huge number of atoms that they are almost indistinguishable. Nevertheless, the Pauli exclusion principle still works. And if I start to fill this crystal with electrons, because each atom donates a certain number of electrons, I would have to put 2 electrons in each state, one with spin up and another with spin down. So the way one fills the bands with electrons is by starting from the lowest energy state and then adding electrons up and down to each crystal momentum state of the band. The energy, the maximum energy that you reach that way is called the Fermi energy. That was named after Enrico Fermi. And if the Fermi energy crosses the band somewhere, anywhere in the middle of the band, what you have is a metal, because in this case, it's very easy to promote electrons in states which are occupied below the Fermi energy and states which are unoccupied, which are above the Fermi energy. So if you apply an electric field, electrons can easily move from low energy states to high energy states and move around the crystal under the electric field. So this is what a metal does. However, if the Fermi energy lies in between 2 bands, okay, in this case, the 1s and 2s, somewhere here, in the region where there are no states. So this is the gap region, okay? It's called gap because there is a gap between 2 energy states. In this case, if I apply an electric field, nothing happens, because in order to make an electron move, I have to pay the energy price of exciting the electron from the low band to the high band. So, you know, these very simple concepts, okay, that were created in the beginning to mid of the 20th century that now seem almost trivial. At the time, they were not trivial at all, because they were direct applications of quantum mechanics to the motion of electrons in solids. Okay, so this is the story. And now, for instance, for us today, we're now on a Zoom talk, so we are all using digital technology. We are using processors, microchips based on silicon, okay? And you hear a lot about semiconductors. What are semiconductors? Semiconductors are essentially insulators that have a gap of the order of the thermal energy. So just by heating up the material, you can excite the electrons across this gap. Okay, so semiconductor is just a special case of an insulator. But nevertheless, strictly speaking, these are all insulators. This is the base of all technology that you have today. That's it. This is all based on these simple concepts that change the way life is on this planet today. And this is why we can communicate even when we are on a lockdown at home, bored to death because we have nothing to do. Anyway, so this is the very basic thing. So now I hope that you understand that dimensionality comes about from the way atoms bind to each other through the states, through the wave functions of the electrons. And that's why, for instance, you can go from, say, a one-dimensional material like a carbon nanotube or a polymer molecule, or you can go to graphene, which is a two-dimensional, or any other two-dimensional material. It has to do exactly because of the way these wave functions organize themselves in space, and you can go from that to traditional three-dimensional materials. This is, for instance, the structure of diamond or graphite, which is essentially piling up these graphene layers together. But by piling up these graphene layers together, you create connections between layers, and therefore the electrons also move along the third direction. So graphite is not graphene, okay? Because in graphene, there is absolutely no motion in the direction perpendicular to the plane of graphene. In graphite, there is. So this is what changes the whole the topic of this dimensionality today. Okay, but all these materials, from the perspective of what I told you so far, they can be metals or insulators or semiconductors. They can be 1D, 2D, 3D, doesn't matter. Okay, it just depends if the Fermi energy lies within the band or lies in between bands. That's it. And this is valid for any material I'm showing in this slide here. So what makes the difference? What makes these materials dimensionality different is that electrons have charge. And from basic electrostatics, you know that charges repel each other through an electric field, right? And this electric field propagates in three-dimensional space. So you can have a material in one dimension, two dimensions, three dimensions, it doesn't matter. The electric field is always three-dimensional, right? And that's what makes different the dimensionality, is the electron-electron interaction that makes everything different. So let's think about a three-dimensional material. Again, this is diamond, and I have a bunch of electrons moving around there, right? Electrons can move from atom to atom, as we discussed before, nothing new. And the first thing you can think, and actually this is how solid state physics started, is that this looks very much like a gas of particles. These electrons move around without seeing each other very much because there is enough space, and they can move around freely. So this is called the free electron model. Arnold Sommerfeld, who was a very influential theoretical physicist of his time, essentially used this extremely simple model to explain why electrons behave the way they behave in solids. Okay, so it's the simplest thing because simply there is enough space for electrons to go around. But now consider the extreme case of a one-dimensional material, like a carbon nanotube, for instance. There is much less space, right? So as the electrons move around the tube, they will always find each other. They will always collide. So the motion of the electrons is so constrained, right, that there are not many options for the electrons to go around. So is an extreme case. So this is a collision pendulum. I'm sure all of you have seen this before. So essentially the energy is going to be transmitted from one side to another of this tube in a very different way that it is in a three-dimensional object, okay? Because of the electron-electron interactions, the collisions between these electrons. Now, 2D is a mixed case because 2D is more like playing billiard balls, right? So everything is moving in two-dimensional space. It's constrained, but not so constrained. But definitely is much more fun, as Tom and Jerry have shown us. So reduced dimensionality leads to more collective behavior. So this is the message here, okay? Because of the electron-electron interaction is essentially enhanced as you reduce dimensionality. One example of collective motion is so-called plasmon. So plasmon is essentially, can be seen as this. When I have a material, and then around the atoms, I have the electrons. This material is periodic, is structured. If I apply an oscillating electric field, I can push the electrons around without pushing the nuclei. Why? The nuclei are very heavy. So one proton is 1,000 times heavier than an electron. Now imagine in a carbon you have 6, so you have 6,000 times more mass there. But what you can do is make this oscillation. If you do it right, you can make all the electrons move coherently. And this coherent motion of the electrons around the background of the nuclei produces what's called a plasma. And plasmons, they have very different dispersion relation, which means energy between their energy and crystal momentum. In 3 dimensions, the energy of a plasma is pretty much independent of the crystal momentum, okay? In 1 dimension, it's essentially linear with momentum. Now, in 2 dimensions is a special case. It's essentially, it goes like the square root of the momentum. So you see the speed velocity is essentially the speed at which the plasma moves is essentially the derivative of the energy with respect to the momentum, okay? Now, a 3D plasma essentially doesn't propagate because the derivative is 0. In 1D, the speed essentially is constant in the material, but in 2D, the derivative of a square root diverges as you goes to very long wavelengths. So essentially, plasmons in 2D become extremely fast, okay, from that perspective, because of this way the energy depends on the crystal momentum. So in fact, in 1D, it was shown by several people, but especially by Joaquin Luttinger many years ago, is that the restrictions for electron motion in a one-dimensional material are so strong that they essentially, electrons do not exist inside of 1D material. What does that mean? It means that if I take an electron and I put inside of a truly one-dimensional material, it will dissolve into collective plasmon-like modes. So essentially, this is to say that the electron does not exist anymore. Electron, as I said, is a fermion. It has the Fermi statistics. It obeys the exclusion principle. These plasmon-like modes that exist in 1D systems, they are like bosons. So you transform, when you put an electron into a one-dimensional material, you are pretty much transforming a fermion into a boson. Okay, so this is called Luttinger liquid. Okay, so it's the name that was given, but for this one-dimensional electronic states in one dimension. Now, this is very extreme, very exotic. This is phenomena that it's actually very hard to measure experimentally, but it has been demonstrated experimentally. Okay, in 3 dimensions, as I said before, these restrictions are very weak. So essentially, when you put an electron inside of a 3-dimensional material, it remains an electron. Okay, it remains. The only thing that happens is that its inertia changes, because now as it moves around, it has to drag the other electrons, it has to drag the lattice. So this is where the terminology effective mass comes from. So essentially, to explain that the electron remains an electron in a 3-dimensional material, but the only thing that happens is that it becomes either fatter or thinner. It loses mass or gains mass, but otherwise it remains an electron. Okay, so it's very extreme what happens between 1 dimension and 3 dimension because of the interactions between the electrons. Now, 2 dimensions, as I said, is exactly in between. So, and in fact, recently in 2 dimensions, we have been able to measure those plasma modes using a technique called scanning near optical microscopy, which essentially you take a very thin object, like the tip of an atomic force microscope, and then you shine light. And using the evanescent waves, the electric fields coming from a light source, a laser or something like this, you can couple the light with the plasmons inside of the material. And what you see are these beautiful patterns that you see here from the essentially the plasmonic waves bouncing out of defects, edges, all sorts of inhomogeneities in the material. In this other experiment here, the same thing. It uses a gold nanoparticle as a launcher for these plasmonic modes. And these plasmonic modes, as you can see, they propagate around the material, forming this pattern. So in this case here, you can see that the plasmons are really real objects. It can be observed with this NOM technique and form these beautiful structures. In fact, it's believed that new technologies for electronics can come out from these plasmons exactly because of this very unique dispersion relation that makes the phase velocity of the plasmons to become very large at very small crystal momentum. So just to give you an idea of these things. Now, let's go to a different topic. So far, we're talking about what happens in metals. What happens in semiconductors? So as I said, it doesn't matter what dimensionality you have. A semiconductor is always the same thing. It's an insulator with a gap of the order of the thermal energy, KBT. Now, the lower band, the one that is occupied, is called valence band. The conduction band, the upper band that is unoccupied, is called conduction band. And the Fermi energy, as I explained, is exactly in between the 2 bands, and there is an energy gap there. Okay, so when you excite an electron from an X state on a valence band to the conduction band, you have to give it enough energy to overcome this gap in between the 2. You create what's called an electron-hole pair. Okay, a hole is an absence of an electron, and being absence of something that was neutral, And given that the electron has negative charge, the hole has positive charge relative to the electron, okay? And traditionally, these electrons and these holes, we assign to them effective masses. Just like in the Sommerfeld model, we think of them as free particles that can move around. But in reality, because they have opposite charge, in fact, they can bind and form states like hydrogen, little hydrogen atoms of electrons and holes. And these are called excitons. So the exciton, there are different types of excitons. These are two. The Vanier excitons are huge excitons where the radius of this hydrogen atom is very large and take over many, many atoms in the lattice. Or it can be very small excitons like Frankel excitons of the order of the spacing between atoms, okay, distance between atoms. Okay, the binding energy depends on several things, the size of the gap and things like that. But the important thing about this concept is that it's, again, the attractive energy between the hole and the electron that makes these bound states. And it turns out that these bound states can be observed and are observed experimentally in many optical experiments where you can excite this electron hole pair with light, okay, like photoluminescence experiments and so on. So to understand the optics of material, it's very important to understand the excitons. And again, you know, from what I told you before, it's more or less obvious that because the electric field propagates in 3 dimensions, but these electrons and holes can propagate in 1, 2, and 3 dimensions, that the effect of the Coulomb interaction is going to be very different. So in 3 dimensions, these excitons just look like beautiful hydrogen atoms, and you can explain a lot of the experiments just by assuming the hydrogen model. But when you go to 2 dimensions, things are rather different, because in 2 dimensions, the electric field propagates out of the plane of motion of the semiconductor. And this changes the whole story. So there are 2 major failures for the exciton model. First is that this effective mass approximation fails, which means that the interactions are so strong that they actually involve states which are far away from the edges of the bands, which means that the Sommerfeld model actually fails. Another thing is that the hydrogen model itself fails. So the hydrogen model is not enough anymore to explain the behavior of these excitons in 2D semiconductors. And in fact, you have to introduce many other types of excitons. This is in this picture here, you can see a traditional exciton. You can form an exciton state, but then you can have bound states of 2 holes and 2 electrons. It's called a biexciton. And then you can have a bound state of 1 hole and 2 electrons, and so on and so forth. So actually, one of the things we see is in 2D semiconductors is that if you try to use the traditional 3D theoretical structure to explain excitonic states in these materials, you have to rely on lots of different bound states. To me, this is a sign that essentially there is a problem. Maybe some of my colleagues will be upset when I say this, but to me, it means that we're not capturing something fundamental if we really need to describe these things. So the Luttinger model is exactly the counterexample. If you go to 1D and you try to, you force to describe the motion of electrons in 1D with a free electron model, it will fail miserably. Therefore, you know, if you try to insist by making more and more and more corrections, you never get the real result. So you have to find non-perturbative ways to describe these materials. And I think with 2D semiconductors, my feeling is that we are exactly at that stage, that we have not been able to fully describe electron-electron interactions in these materials. So this has a very strong consequence for technology, because if we are going to build technology based on 2D materials, then we are going to need to understand the fundamentals of things like excitons in these materials, because they have a direct effect in the properties of the semiconductors, in the way they interact with light, and so on and so forth. Okay, let me change now to another topic, which is very close to my heart, which is magnetism. So everybody here knows what a magnet is. So this is an example of a magnet. And if you put a magnet with some iron powder around, it forms these beautiful patterns. And one thing that we know is that if you heat up a magnet like this, it loses its magnetization. So essentially, if you look at the magnetization as a function of temperature, the magnetization drops as a function of temperature. And eventually, if the temperature is very large, the magnetism goes away. So where does this come from? It comes from the fact that in magnetic materials, you have magnetic moments, like the spin of the electron. At high temperatures, these moments, these little uh, 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 magnetic moments, they are all disordered. They are moving because of temperature in all directions. So you don't have magnetization. But as you lower the temperature, these states, they can order. And this is when you get a magnet. If all the magnetic moments point in the same direction, you get a ferromagnet, which is the case shown here. But there are many other types of magnetic order. For instance, you can have what's called antiferromagnetic order, where you have one atom pointing up and another atom pointing down. The total magnetization here is zero. You don't have a permanent magnet. Nevertheless, you have magnetism inside of the material. So actually, these concepts were studied also in the 20th century. The critical temperature of a temperature at which the magnetization ends for a ferromagnet is called the Curie temperature. This is due to Pierre Curie. He was a husband of the famous Marie Curie, in whose family there are, I don't know how many Nobel Prizes, maybe 3 or 4. And then there is the critical temperature for an antiferromagnet is due to Louis Néel, who essentially was studied the behavior of these magnets. Okay, so this is the classical view of magnets, and it's all based on three-dimensional magnets. Now, what happens when you change dimensionality? 1D magnets are the extreme example. So there are examples of one-dimensional magnets in nature. These are usually like molecular crystals, where you can have antiferromagnetic order, spins pointing up and down, or ferromagnetic order, all up. But one thing about these systems is that they can be easily disordered. And the disorder has essentially two, you can disorder traditionally by increasing the temperature, or you can disorder by quantum fluctuations. Essentially, there is a tendency in these magnets to form what's called topological defects, which are essentially solitons, which can propagate along these magnets and destroy the magnetic order. So magnetic order in 1D is highly affected by quantum mechanical motion of the magnetic moments. Now, in 2D, again, is a case in between. So there are materials like chromium triiodine, which has this beautiful structure here. The chromium atoms have a magnetic moments, and it's exactly a mix. You can have ferromagnetic order or antiferromagnetic order, but now this magnetic order is essentially distorted by two-dimensional topological defects, like the ones I show here: skyrmions, merons, anti-skyrmions, anti-merons, and so on. And this is also an effect of quantum mechanics. Nevertheless, they are more resilient than 1D magnets to get order, but less resilient than 3D magnets. So again, dimensionality plays a big role. So since my time is up, let me conclude here. So I want to show you that dimensionality plays a fundamental role in the properties of materials because of electron interactions, that this model of electrons moving freely works well in 3 dimensions, but fails miserably in 1 dimension. And 2D is actually the forefront of research in terms of understanding how electrons interact with each other. So today, I only want to give you a taste of what's out there. There is much more out there. If you are interested in knowing more and in the near future, we just wrote an article that it's going to come on Nature Review Physics. So you see Alexander Rodin, Maxim Turchin, and Alexandra Carvalho are my collaborators in this paper. So wait and see and read and enjoy and have a good time working with materials. Thank you very much. So after that, I think we have time for a few questions. Let me see here the questions. First question, are the slides recording available after the section? Yes, they are available. We're going to post the whole seminar on YouTube in our site. Yes. Oh, Andrew Wee. So Andrew is asking, what are interesting fundamental questions to D magnets and what do you think are the potential applications? So I think that is what I said during the talk. I think that the interesting thing is exactly this interplay between dimensionality and interactions. And from the perspective of physics, you have the opportunity to deal with new types of excitations, like these skyrmions, mesons, and so on, and use them in interesting ways, maybe for spintronics, maybe for media recording, maybe for several different things. But this is a field that's really in its early days. So I think it's going to take some time for us to really know where we're going to go in terms of applications. I think at this point, we're really exploring the basic science, and it's a lot of fun. Okay, any more questions? Let's see. Okay. David Isidi is asking, from the slides describing the magnetic alignments, how would super paramagnets look like? They would look very much like normal paramagnets. I'm not sure if I know any super paramagnet in 2 dimensions. I would have to go back to you on that one. I have to think a little bit, but I don't know. Okay, wow. Let's see. We've got lots of questions now. Enrique Rosa is asking me, can you comment on the exton pictures in 1D? Is it as clear and diverse as in 2D? The answer is yes. The answer is yes. And there is a whole literature on that in the context of carbon nanotubes, for instance. But I think very little has been done in terms of understanding the interactions in excitons in 1D. I may be wrong, but I think it's something we should definitely take a look. It's very interesting. Stefan Roche, are you thinking to generalize the Luttinger heuristics to 2D for trions, for instance? Stefan, no, but the young people who work with me should be doing that. I think this would be very exciting if they can do that. maybe you can do that too. Okay, Alexei Berdugin. How can one probe or did probe the interactions in 1D wire and check the Luttinger model? So there are many tests. okay, over the years. You know, usually it's not so simple to do this. Most are based on tunneling, because if you tunnel an electron from a chip, right, for instance, scanning tunneling microscope, for instance, into a 1D material, the way this tunneling occurs depends on the spectral function, which means how much of the electron is left in the collective of the 1D system. And there are many experiments in this direction. And there is actually a big literature, like maybe 20 years ago, this was a very, very hot topic. But when graphene came into play, it's essentially wiped out all the literature, because all these people moved into graphene. Maybe it's also a good topic for us to revisit, especially if we think in terms of interactions between 1D and 2D materials. Xin Yuan Wang, does Moiré pattern only play a small perturbation to the Hamiltonian of a 2D bilayer structure? What else can it change? Okay. This is a very interesting question, and I tell you why. Many years ago, when people were studying graphite, they thought that the interaction between layers in a graphite stack was so weak, was mostly van der Waals. There was almost no covalent bonds, that this interaction would do nothing. Then when we started working on the bilayer graphene, we realized that it was all wrong, that actually the covalent bonds between two layers of graphene in a Bernal configuration, which is the lowest energy configuration, makes a huge difference in the band structure. All those massless Dirac fermions disappear, you start having massive electrons again, and the whole physics changes, tunneling changes, spectral functions changes, everything changes. Then people start looking at twisted bilayers. So twisting the two graphene layers makes the registry between carbon atoms less precise. And therefore people said, okay, so twisting the bilayer doesn't change much. And then people showed experimentally and theoretically that that's not true, that the twisting the bilayer creates what's called Van Hove singularities. And these Van Hove singularities, it's increasing the density of states. And then people showed that these bands can be extremely flat, and therefore very, very localized. And this could lead to new things. And in fact, a few years back, superconductivity was discovered. And superconductivity is a direct effect of that interaction between layers. Okay, so this is very open field, lots of things to do. And I hope you have as much fun as I have on that. I want to thank you very much for your attention. It was a pleasure to be with here today. Be safe, be healthy. And next week, we have a very special guest, Professor André Gaim, who also got the Nobel Prize with Konstantin Novoselov, is going to be here with us. I don't know what he's going to talk about, but I'll find out and tell you soon. Thank you so much. Have a great day ahead. And good night for the other people in the other side of the world. Take care.